This section is on the Kruskal-Wallis test. This is a non-parametric test used to determine whether samples originate from the same distribution, and it is similar to the ANOVA test. So first, we have to verify that the samples are random, the samples are independent, and that the data can be ranked. Next, we combine the data from all the samples and sort the data from smallest to largest. We rank the data, and ties are handled by finding the mean of the ranks for tied values. Also, we label which sample the data comes from. Then we state the claim and the null and alternative hypotheses. Now the null hypothesis always states that the distributions of the populations are the same. The alternative hypothesis always states that the distributions of the populations are not the same. Then we identify the level of significance, the critical value, and the sample sizes. Capital N is the sum of the sample sizes. Then we find the sum of the ranks from the three different samples, and then we square these values. To find the test statistic H, we use this formula. Then we compare H with the critical value. If H is greater than the critical value, we reject the null hypothesis. If H is less than or equal to the critical value, we fail to reject the null hypothesis. Then we write the correct conclusion. 3 random samples have been obtained. At the 0.05 level of significance, is there enough evidence to support the claim that the distributions of the populations are different? Use the Kruskal-Wallis test. So first, we need to combine and sort the data. So the lowest value is 9, and that's found in samples 1 and 3. Next is 11 from sample 2, 12 from samples 1 and 3, 13 from samples 1 and 2, 14 from sample 3, 15 from sample 3, 16 from sample 2, 17 from sample 1, and 18 from sample 2. Now we need to rank these. So there's a tie for the first and second rank. So we need to take the average. So 1 plus 2 divided by 2 is 1.5. So both 9s get a rank of 1.5. 11 gets a rank of 3. There's a tie for the 4th and 5th positions. So if we take the average, we get 4.5. So both 12s get a rank of 4.5. There's a tie for the 6th and 7th rank. So both 13s get a rank of 6.5. Now, there's no more ties, so the rest of the ranks are just 8, 9, 10, 11, and 12. The claim is that the distributions of the populations are different, and this is the alternative hypothesis. The null hypothesis is that the distributions of the populations are the same. Alpha is 0.05. Now, for the critical value, let's look at the table. Now, since all 3 samples have a size of 4, the critical value is 5.6923. Now all 3 sample sizes were 4. Capital N is the sum of all of the sample sizes, so that is 12. R1 is the sum of the ranks from sample 1, and that is 23.5. And if we square that, we get 552.25. R2 is the sum of the ranks from sample 2, and we get 31.5. If we square that, we get 992.25. R3 is the sum of the ranks from sample 3, and that's 23, which, if we square that, is 529. Next, we need to use this formula to calculate h. So it's going to be 12 divided by 12 times 12 plus 1, multiplied by 552.25 over 4, plus 992.25 over 4, plus 529 over 4. And then we subtract 3 times 12 plus 1. Now I want to look at that middle part on the calculator. So type that into the calculator, and we get 518.375. So we have 1 over 13 times 518.375 minus 39. And that's equal to 0.875. So h is less than the critical value. So we fail to reject the null hypothesis. And the conclusion is, at the 0.05 level of significance, there is not enough evidence to support the claim that the distributions of the populations are different.